Hello. In today's topic, we're going to be discussing something called binomial experiments and the associated probabilities. As we'll see, a binomial experiment is an event where we have two possible outcomes. That's where the bi in binomial is going to come from. This whole unit we've been working through probabilities, so this is a special type of probability that we'll be looking at today. To kind of get us introduced to the topic, I'd like you to consider the following warm-up question. It's connected to something that will occur later in the discussion. So rotator cuff surgery is going to be performed on 3 patients. How many different ways could the 3 surgeries have exactly 2 successes and 1 failure? So I'd like you, if you want to, you can pause the video now, think through it. Otherwise, I'm just going to go. So I would imagine most people would probably just construct the sample space. You could have success, success, failure. You could have the failure occurring on the second one, or you could have the failure occurring on the first one. So you'll see that there are 3 ways. It actually, you could count this not by making a sample space. You could use our combinations that we've been talking about recently. It's the exact same as doing 3 choose 2. If you type in a calculator 3 choose 2, you're going to see the output is 3. There are 3 ways to select 2 successes from 3 outcomes. And this will come up to later in the topic. So kind of just hold on to that thought. Moving forward, we should probably define what a binomial experiment is. So there are many probability experiments for which the result of each trial has only 2 possible outcomes, a success or a failure. Such an experiment is called a binomial experiment. Because these occur so often, they have their own section in our study, and they have their own vocabulary term in the field of statistics. They're called binomial experiments. A binomial experiment is a probability experiment that satisfies the following conditions. Condition number 1, the experiment has a fixed number of trials, where each trial is independent of other trials. Fixed meaning we set the number of trials from the onset, and the outcome of one does not have an effect on later trials. Condition number 2, there are only 2 possible outcomes for each trial. Each trial is either a success or a failure. However, we depend on defining those items. Condition number 3, the probability of success, which we will denote P of S, is the same for each trial, and that's because they're independent. The success of one shouldn't affect the success of another. So same probability each time. Last part, the random variable x counts the number of successful trials. So you can either have 0 successful trials all the way up to n, which is the number of trials that you had from the beginning, which is condition number 1. So those are all the conditions that make a binomial experiment. If there's an experiment that satisfies all 4 of those things, it is a binomial experiment. When working with binomial experiments, we use the following notation. So n stands for the number of trials that were going to be repeated. Little p stands for the probability of a success in each trial. Lowercase q stands for the probability of a failure. You'll note that the probability of a failure is equal to 1 minus the probability of a success. For example, if there's a 30% probability of success, then 1 minus 0.3 would tell me that there's a 70% chance of a failure. So they complement one another in making 100%. Last part, little x, is the random variable that represents how many successes we have out of n trials. So for example, if we ran 15 trials, x could be any number between 0 all the way to 15. Those are the number of successes that we could have. We're going to look through a variety of situations and just state whether they're a binomial experiment or not. And if they are, we're going to practice stating what n, p, q, and x are. So situation number 1, you pick a card, note whether it is a heart or not, and replace it. You pick 5 cards and want 2 to be hearts. So the first thing is, yes, this is a binomial experiment. The reason why is we have a fixed number of trials. You go down the list. The big thing, though, that you're really looking for is whether the success changes for each trial. And because we are replacing, and that was key, because we're replacing the cards after looking at it, the probability of getting a heart for each draw is the same. It's 25%. So because we're replacing it, the probability of success never changes, and we have a binomial experiment. Binomial because we have only 2 things occurring, either a heart or not a heart. How many trials are we doing? It says we pick 5 cards, so 5 trials. Probability of success is 25%. That's 13 out of 52. The probability of a failure is 75%, which is 39 not hearts out of 52. And we want 2 successes, so x would be 2 hearts. Situation number 2. You take a 10-question multiple choice quiz with 4 options for each question. Randomly guessing, you want to get 5 correct. Well, this is a binomial experiment. There's only 2 options. You either get the question right or not, so it's binomial. The big thing is that you're always looking for really is whether there's the probability of success is the same for each event, for each trial. And it is, because you're guessing each time, you have a 25% likelihood. So this is a binomial experiment. Fixed number of trials and all the conditions apply. There are 10 questions, so the number of trials is 10. Probability of success is, it says 4 options, so 25% again, but for a different reason than the one above, really. Three options are going to be incorrect, so 75%, and we want to get 5 of them correct. So 5 trials will be correct. Success. Last one, you draw 5 cards one at a time and do not replace a card once it is drawn. You want 3 of the cards to be red. This is not a binomial experiment. And the reason why is because you do not replace the card. So the probability of success for each trial changes because you're not replacing. Because you do not replace the card. And so because each trial doesn't have the same likelihood of success, this is not going to be a binomial experiment. You have to use different techniques in order to calculate that probability. I'm going to give you a chance to try. So exact same thing that I was doing. State whether each is a binomial experiment or not. If so, state N, P, Q, and X. So pause the video now. Give yourself a chance to try. Okay, the first one, it is. Survey found that 49% of U.S. households own a video game console. 20 households are randomly selected, and you want 8 of them to own a console. Without any more information, there's no reason to believe that one household owning one and then you randomly select another household is going to have an effect between one another. So this is going to be a binomial experiment. 20 households, 49% likelihood of owning a console, which means 51% will not. And we wanted 8 of them to own a console, so that'd be 8. And this last one is a no. The reason why is because the way that the state lottery works, once one of the balls has been selected, they don't put it back into the urn. So the probability of success changes for each time. So this is not going to be a binomial experiment. Now we're going to calculate probabilities for binomial experiments now that we know what a binomial experiment is. So rotator cuff surgery is successful about 75% of the time at a said clinic and is said to be performed on 3 patients. What is the probability of the surgery being successful on exactly 2 of the patients? First of all, is this a binomial experiment? Yes, we're assuming it's 75% likelihood for each one. The probability of one doesn't affect the probability of the other. There's a fixed number of trials, 3 trials. We want to know what's the likelihood of getting exactly 2. So since it is, we can find the probability by making a probability tree. So this is what we're going to do. We'll say for the first surgery, you can either have a success or a failure. The second surgery, success, failure. Third surgery, success, failure. And so I list all of the different outcomes, success, 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 failure, success, all of them. I can see that there's going to be 1, 2, 3, 4, 5, 6, 7. There's 8 different outcomes. And now I'm going to calculate the probability for each of them. So as I'm going down the tree, if you wanted to, it said 75% chance of success. So this is a 0.75, this is a 0.75, and this would be a 0.75 if you wanted to fill it in the tree. Failure is 25%, so 25 here, 25 here. And then you could fill it in for each, every single one of these branches of the tree. I just want to look at one of them real quick. Let's say you do success, success, success. You'll see I calculate that probability of as it being a 75% times 75% times 75%, 3/4 times 3/4 times 3/4. That's 27 out of 64. Now I'm just going to go looking to find all of the different ones that had exactly 2 successful surgeries. And that was this one had 2 successful, this one had 2 successful, and this one had 2 successful. If I look, all of them had a probability of occurring as 9 over 64. And so all I need to do is do 9 over 64 plus 9 over 64 plus 9 over 64, or just do 3 times 9 out of 64. There were 3 ways to get 2 successes. Each of them had a probability of occurring 9 over 64. Where did I get that? It's because each of them had 2 successes, so 3/4 and a 3/4, and 1 failure, so multiply by 1/4. That's where you get your 9/64. So I found about 42% likelihood that we're going to get exactly 2 successful surgeries. This binomial kind of tree it's a lot of work, and you can imagine if I had more cases, this tree would get huge and this diagram over here would get large. So instead of doing that, we're going to be more clever. Instead, what we're going to do is we're going to use what's known as the binomial probability formula. And I'll show how it's interconnected really to the tree that we made just a second ago. So really, it's unnecessary to construct a tree diagram every time if you realize the underlying structure. Instead, we can use the binomial probability formula. The binomial probability formula states the probability of exactly X successes in N trials, and this is what it does. The very first piece is this piece. It calculates the number of ways of getting X successes out of N trials. In our last case, that was 2 successes out of 3 trials. That was 3 choose 2 right here. So, 3, let's use different color. 3, choose 2. We did this as a warm-up. That's 3, and that's where that piece came from right there. So the first thing I do, calculate the number of ways to get X successes from N trials. Then what I do is I multiply the probability of X successes. So probability of success in our last case was 75%, and I need to square it because I have 2 successes. That's like if you look at this branch right here, I had success, success. So really it's 3/4 times 3/4. We could write that as 3/4 squared. But I also need to get some failures. This last piece, so this middle piece right here, is the probability of getting X successes, and this last piece is the probability of getting our number of failures. The number of failures is going to be the number of trials minus the number of successes, N minus X, or really you can just think about it as the number of failures. So this last piece is the probability of getting our number of failures. We just had 1 failure in our case with the tree. That's why there's only 1/4 in all of the highlighted situations where there was just 2 successes. And that's the probability formula. We'll do it real quick right here for that rotator cuff surgery one, just so you can kind of see it all develop. So there were 3 trials. I want 2 successes. Each trial has a 75% chance of occurring successful and a 25% chance of being a failure. If I want to calculate the likelihood of getting 3 successes, the very first thing I'm going to do is calculate how many ways can I actually get 2 successes out of 3 trials. So I'm using the formula. So the formula is this: C N choose X times probability of X successes times Q failures. They said N minus X here. So first piece, from 3 trials, how many ways can I get 2 successes? So you grab a calculator, you type in 3, choose 2, or you saw from our warm-up, that is going to be 3. Next piece, I need 2 successes. Each success has a 75% chance of occurring. So 0.75 squared. That will go right here. And each trial has a 25% chance of failing. So I need 1 failure. So I'm only going to multiply by 0.25 once because there's only 1 failure. And I grab a calculator and do it. You can type in 3 times 0.75 squared times 0.25. For sake of time, I'll tell you it is 0.422. You can trust me on that because the calculator is going to serve another purpose here in a second that I'll show you, because there's a built-in function for this formula. So it's going to be 0.422. Okay? Because binomial experiments occur so frequently, there is a built-in shortcut into the calculator for a prior situation, and it works like this. You have to go to second and then choose distribution. Then you enter the information in the following order. You type in trials, probability of any trial being successful, and then the number of successes that you had. So for ours, it'd be binom, PDF, binom standing for binomial. PDF, you don't really need to know, but in case you want to, it stands for probability density function. It's a function because I give it conditions and it outputs for me the probability. So if I grab the calculator, I can check it out. So distribution, you have to hit second, and then it's right under the vars button. So hit second, distribution. I believe you can scroll down, or you can go from the top and kind of wrap around. It is binom PDF, and be aware there's something called binom CDF that we'll use also here in a little bit, but choose the A option, binom PDF. So binom PDF, the first thing it asked me for is number of trials, 3 trials. Probability of success on any trial is 0.75. How many successes would I like? I would like 2 successes, and then I hit paste and ask it to run it, and there it is, 0.422. Be aware, if you're using a TI-83, you have to actually type in these values. You'll have to do binom PDF, and then you have to type in this last part. That calculator is too old. It doesn't prompt you for those. You have to type those in. Okay, so just to practice these a few more. So a baseball player has a lifetime batting average of 31% essentially. Suppose in the next game he's going to get 5 at-bats. What's the probability he gets exactly 3 hits in scenario number 1? Well, first off, this is a binomial. It's a binomial because we have a fixed number of trials, 5. We want to know how many successes, 3. Each time he goes to bat, we're assuming he has a 31% chance of success, which means he has a 69% chance of failure. So if I want to know the probability of him getting exactly 3 hits, well, n would equal 5. P would equal 31%, Q would equal 69%, and we have 3 successes. So I grab my calculator, I type in binom PDF 5. I have to remember the order. It was NPX. And then probability of success is 31. You don't need to tell it the percent of failure because it knows if it's a 31% success, it can get to the 69% failure. And I need 3 successes. So I grab my calculator, I go binom PDF, and I type in, it was 5 at-bats, 31% success. We want exactly 3 hits, and I hit paste, and it's going to give me about a 14.2, 0.141. Or 2, I think, if I round. Is that right? Yep. So 14.2% chance he's going to get exactly 3 hits. What's the likelihood that he gets 4 or 5 hits? Well, 4 or 5 hits, I'd have to find the probability of getting exactly 4, the probability of getting exactly 5, and then in probability, or means addition. So this is going to be binom PDF 5, 0.31, 4, plus binom PDF 5, 0.31, and then 5 hits. And then I calculate each of those individually, then I'm going to add them together. So grab my calculator. Binom PDF, so 5. The only thing I need to change here is we wanted 4. So that, I hit enter. So that's a 0.32. Find that piece. Now I'm going to add it to the second part. So again, go to binom PDF. This one was, the only thing I need to change is I want 5. So take my binom with 4, add it with 5. When I add the 2 pieces together, I go slightly up. You'll see it looks like I can use this now to know, hey, when it was 4 successes, I had a 3.1% chance. Now with 5 successes, I have a 3.4% chance. It only went up by 0.3, not very much, because it's highly unlikely that they're going to get all 5 hits in 5 at-bats. So total 0.035, maybe if I round it, 0.035. Last one, 3 or less hits. So 3 or less hits, that would mean I'd have to find the probability of getting 0, 1, 2, or 3 hits. And that's a lot of calculating. So this would take 4 things to add together and then add them all up. But the calculator has a shortcut for this. It's called the binom CDF. So the binom CDF does all of the cases that are equal to or less than that number of successful trials. So if I go to my calculator and I type in 5, 0.313, but I use CDF. I'll show you where that is. You go second, distribution. It's this one right here. You're choosing option B. CDF stands for continuous. You can kind of think about it as like a combined. So it does all the probability of getting 3 or less, and you run it, and you'll find that there's about a 96.5% chance that they're going to get 3 or less. And there's actually, look at this. These two numbers, if you add them together 100%, because this is getting 4 or 5 hits, this is getting 3 or less, and that's all of the possibilities. So technically, you could have used the answer for B to get C by just doing 1 minus 0.035, because they're complements of one another. So that's how the CDF part works. I'm going to give you a chance to try with something that was actually kind of occurred in the news. So familiar site greeted Carolina Panthers safety. So this is an NFL scenario with some steroid testing. Safety Eric Reed as he walked into the locker room following a 12-9 loss to New Orleans Saints. This occurred on December 17th of 2018. It's said, you have been randomly selected by the NFL drug testing program's medical advisor to complete a urine doping test today. The small slip of paper informed him. He shared it on Twitter. According to Reed's count, that made 7 drug tests for the 27-year-old despite only being a member of the Panthers organization for 11 weeks, which sure seems like a lot of drug tests for a program that is supposed to randomly select a small group of players each week. Of course, Reed doesn't seem to think that they're random if he's been selected 7 out of 11 weeks. So he says, I've been here 11 weeks. I've been drug tested 7 times. That has to be statistically impossible. I'm not a mathematician, but there's no way that's random. So I looked into it, and I'm going to give you the information for you to determine if this is actually random. There are typically 72 players eligible for drug testing on each team each week, and the NFL states a computer randomly selects 10 of those players. So that means success is 10 out of 72. So there's about a 14% chance that he's selected any week. What is the probability that in 11 games, Reed would be randomly tested 7 or more times? Does he appear to have a case that there's discrimination? So we want to find the probability that there were 7 or more successes. Well, instead of finding 7 or more, I can find 6 or less and then subtract those. And I can use this binomial in order to calculate that. So give it a try, come back, see how you did. So this is what you should have found. You should have found 1 minus binomial CDF for 11 weeks, 13.9% chance of success, 6 or less times that he would have been drug tested. If you do 1 minus it, you find the answer is 0.000197 or 0.0197. That's about 0.02%. That's about 2 10,000ths or a 1 in 5,000 chance. So there's only about a 1 in 5,000 chance that he would have actually been tested as many times or more than he was, which means it definitely looks like he has a case of there being discrimination. So that is it for today. Thank you very much and have a good day.